So, in this lecture we shall be looking at some of the case studies of some modern day processors that we see around us. So, we shall be basically looking at two such case studies. One is that of a so called graphics processing unit or GPU, and the other is we will be looking at very briefly the evolution of the Intel class of processors. Okay. So, the title of the talk is some case studies. So, we start with GPU. So, first let us try to explain what a graphics processing unit is. Well, traditionally GPUs were used as a graphics accelerator card to a processor, because with the years the requirements and the demand of graphical processing, video, multimedia has increased. So, the processor, with the help of its own instructions, it will become very difficult for it to handle all the graphics processing tasks. So, what was the trend? That a separate chip or a processor was used which was dedicated for all the graphics, multimedia, animation kind of applications. That has come to be known as GPU or graphics processing unit. Okay. So, GPU is a processor which is optimized for graphics computations both in 2 and 3 dimensions. So, these processors have some very specific features which help in video processing, visual computing, etc. Now, essentially a GPU is a highly parallel, highly multi-threaded multiprocessor. So, we talked about parallel processing briefly earlier. So, GPU is like a very highly parallel computer architecture which resembles the SIMD or single instruction multiple data kind of processing, where there are a number of simple processors which are under control of a single control unit. So, the idea is something like that. So, with the help of very specific instructions, it can provide real time rendering of videos and similar applications. So, it can process image, it can process video. Now, the interesting thing is that because of its inherent architecture, it is a highly parallel SIMD machine. So, why use it only for graphics? We can also use it as a scalable parallel computing engine to execute some applications where very high level parallelism is there. Now, in general we can have a heterogeneous computing system where the parts of the computation which can be parallelized can run on GPU, while the other part can run on the conventional CPU. So, you will see such computer systems available today where CPU and GPU are residing inside the same box, where the GPU is not looking after the graphics, but it acts as a parallel co-processor to the main CPU. Okay? Fine. So, some of the characteristics of GPUs is that, so as I said, it is based on the SIMD mode of computation or processing. So, there are a large number of arithmetic logic unit. So, when I say large number, it goes in the order of thousands. So, in a normal CPU we talk about 2 core, 4 core or 6 core, but here we are talking about thousands of very simple processors which are basically arithmetic logic units. So, such kind of an architecture can be used in application where you are processing on large arrays or vectors of data and there is highly parallelism or parallel mode of computations available in the application. And not only these ALUs, so each such processing unit also contains some small local memory, so that some local data can be loaded and processing can be carried out parallelly on all the processing units. Yeah, and here of course, there has to be a more sophisticated load store unit. So, from the memory you may have to load a vector or array of data. Similarly, you may have to store a vector or array of data. Okay? Fine. So, here as I said, today you have many parallel computing systems which are available in the market, which combines CPU and GPU. So, for applications where the number of threads are very less, which does not use multi-threading to that extent, CPUs work better, because CPUs with a few threads are much more efficient, their instruction sets are much more powerful, their operation latencies are also less. But if you think of programs which has thousands of threads, let us say, then running them on a CPU may not be that efficient. So, here GPUs come into the picture. So, GPUs can provide very high throughput for multi-threading kind of application where the number of threads are very large. So, as I said earlier, that there are applications which may use both kinds of computing. The sequential parts can be running on the conventional CPU, and the numerical intensive parts which are heavily multi-threaded, they can run on GPUs. So, there are GPUs which can consist of up to 1000 cores. So, here I am showing a typical figure 100, and each of the cores can support multiple threads. So, a huge number of threads can be supported in parallel. Now, I am showing you a typical architectural diagram of a GPU. This is a very typical picture. So, you see the processors are divided into clusters, they are not all placed together, they are placed in clusters. Now, in this example you can see each cluster is having 8 plus 8, 16 cores. Okay? Each of these having 16 cores, and there are 8 such. So, 8 into 16, there are total 128 cores here. Now, each of these clusters is having a data cache from where data can be loaded and stored, and there is a bus that connects these clusters to load store units. Now, to increase the bandwidth between the memory and these cores, there can be multiple load store units which can run in parallel. Okay? So, here I am showing there are 6 load store units. There is a thread execution manager, this is more into the software part I am going. So, the threads can be scheduled on these clusters, and inside the cluster there will be a simple operating system kind of a support, where depending on the available cores, so a thread will be running on one of the cores, right. So, there is also a feedback path. So, as a result of computation, the thread manager can be informed and thread manager can act accordingly. So, you see architecturally what we have. So, we have a highly parallel computing system where the so called cores can be very simple as compared to a normal processor core, but suppose there are 128 cores, I can potentially carry out 128 multiplications at the same time, I can carry out 128 additions at the same time. This is the advantage of vector or array processing which I can have. Okay. Well, let us digress a little bit. Let us look into one question that might have bugged you earlier, that the x86 family of chips, which you know are based on the complex instruction set or CISC architecture, do they use microprogramming? Because there is a dilemma which I talked about earlier. So, we discussed, so towards the beginning of the class you have seen that the RISC architectures, they provide you with an implementation which on the average runs faster than an equivalent CISC architecture platform. So, a program will run faster on a RISC architecture as compared to CISC architecture. This has been found through experiments. Now, the question is, because of legacy reasons, because of the requirements of backward compatibility, the Intel series of processors which are the most widely used in the world today, they have to be stuck with the CISC kind of architecture. So, are they compromising on poorer performance? This is the question. Okay. So, the dilemma that I am talking about is that this one I have said RISC architectures execute instruction faster than CISC, but RISC architecture can be efficiently implemented using hardware control. But in a CISC architecture, because of the fact that some of the instructions are very complex, so if you want to build a pipeline directly from there, the pipeline may become quite complex. So, there can be a somewhat compromise, you can say, you can make. So, where the complex instruction sets, so you can use microprogramming to break them up into simpler instructions, and at the next level you can have a RISC kind of an architecture which will be executing the simpler instructions using a combination of microprogramming and hardware control. Okay. So, what I have said is that the Intel processor chips, they are based on CISC instructions. They use in the first step microprogramming to break the complex instructions into simpler sub operations. But here you may note that all instructions need not be broken. There may be some instructions which are already like RISC kind of simple instructions. They need not have to go through this. Okay. These sub operations are very similar to RISC kind of instructions. So, at the high level, at the level of the CISC instructions, so you can regard that we are using microprogramming. But after the instructions are broken up into this RISC kind of instructions, now at the lower level you may consider that there we are using hardware control to execute those instructions in a very efficient and compact pipeline. Okay. So, pictorially it can look like this. So, you have the CISC instructions at the top level, then you have microprogramming which will be translating them into simple operations which are RISC like instructions, which in turn will be executed on a pipeline. Okay, here I am showing the pipeline of MIPS 32. So, that will be something similar to this. So, you just using hardware control, you can execute these RISC like instructions on the pipeline. This is how instructions are typically executed in a modern day Intel processor. Okay. Now, we shall be looking at the evolution of the Intel processor. Of course, we shall not be going into the details because it may involve a lot of advanced topics which you have not covered in the class. I shall be trying to give an overview that how this evolution has taken place and what are these different families. I mean, you have been hearing that this Intel processor families, they are coming through so many generations, Nehalem, Ivy Bridge, Sandy Bridge, so many names you hear. So, what are these actually? Okay. So, let us very briefly go through this. So, the point is that over the years there have been architectural advancements that have taken place in the Intel processor families. So, some of the earlier architectures were called Netburst, which was not so popularly known. Then Core, you have seen the Core 2 Duo kind of processors, you must have heard of it. Then Nehalem, Sandy Bridge, Ivy Bridge, Haswell, these are some names you may have heard. Okay. So, let us see very briefly what are the features. The first of these architectures, the Netburst architecture, well, the first thing was that it used hyperthreading. So, what is the concept of hyperthreading? Well, it uses some kind of virtualization where a single processor, it appears to be two logical processors. So, as if two threads are running on the same processor. So, to the threads, the processor seems to be a separate dedicated virtual processor. So, because we have two threads, you can say that there are two virtual processors which run those two threads, right. Now, there are some differences here. Well, hyperthreading support was built in the hardware, like, so each of these logical processors, they had their own sets of registers, which means we had two different register sets, one for thread 1, one for thread 2, like that. Now, by doing this, resource utilization and performance can be improved to a great extent, because you see, like whenever you use multi-threading with a single set of registers, so when you switch from one thread to the other, you may have to save some registers and restore the new registers. But here, because there are separate set of registers, thread switching is very fast. You simply switch to the other register set. Okay? Well, there is another concept here which is called the rapid execution engine, where ALUs were running faster than the processor. So, the ALU clock was running at twice the frequency as compared to a processor clock. So, the basic integer operations, they were executing in half the processor clock tick. Now, this essentially, if you just correlate with the MIPS 32 architecture, the pipeline, you are trying to say is that for multi-cycle operations which are there in the EX stage, you are trying to reduce that time to half, that EX stage executes faster. Okay. So, this will result in higher throughput and of course, reduced latency of execution. And here there was not much consideration on reducing the number of stages in a pipeline to convert it into a RISC kind of an architecture. So, it had a very complex pipeline comprising of 20 stages, where the complex instructions were directly mapped and executed. So, for branch instructions, because of the deep pipeline, branch mispredictions were pretty high, but because of the simpler stages, the clock frequency could be made very high and performance could be made reasonably on the higher side. And various techniques to hide the various kinds of penalties in the pipeline were also implemented. Parallel execution using superscalar kind of processing, buffering particularly in the load store units, and speculation. We have already seen in branch you can speculate, you can assume taken, assume not taken, like that. And by special hardware control, instructions were executed dynamically and also out of order. What is the meaning of out of order? Like for example, say you are fetching some instructions. Well, here you may find, or the hardware will find, that one of the instructions cannot start execution because there is a hazard. It requires an operand which depends on an instruction which is already executing. So, what it will do? It will go to the next instruction and see that whether we can execute the next instruction. If it finds that the next instruction is an independent instruction which can be executed, so it will be executed first, it will be fed to the pipeline. This is called out of order execution. So, next came the so called core architecture. So, the multi-core architecture came from this family. So, here you had multiple cores and again hardware visualization by using multi-threading. Here the pipelines were made simpler. Instead of 20 stage in Netburst, it became 14 stage. And dual core design, so the first version uses 2 cores, they had dedicated L1 cache and shared L2 cache. So, L3 cache was not there in this family. Okay. There was a concept of macro fusion, where 2 program instructions logically can be executed as one micro operation, one in the first core, other in the second core. This is a high level view. Well, it started to use some intelligent power capability, where runtime power consumption of the execution code was measured and accordingly it was controlled. Well, the temperature was also sensed. Depending on the temperature, the speed adjustment was done. Okay. There are a lot of sophisticated features which are incorporated here. Then advanced power gating for low power. So, some individual processor logic subsystems were turned on and off depending on whether they are required or not. And there was a separate prefetching unit which was extended to support instruction fetching by 2 cores in parallel. Okay. Then came the Nehalem architecture, which is the beginning of the kind of cores that we see today, I3, I5, I7. These have been very commonly used terminologies to us today. So, it is from the Nehalem architecture the family of processors was introduced. So, core I7 was primarily meant for business and high end consumer markets. Well, of course, the time has changed. Today, we want these I7 processors to be used inside our laptops also for daily use. Okay. So, the cost has gone down, power consumption has gone down. So, we can afford to do these things. Similarly, I5 was meant for mainstream consumer market and I3 for entry level market. And some of the features of Nehalem which started to appear was that the memory controller was integrated within the chip and the power management was made more sophisticated. There are multiple power states like high power, medium power, low power. So, the operating system can initialize the power state of the processor and accordingly run your programs on that power state. So, depending on that you can conserve battery or you can run your application faster, whatever you want. And there were several improvements made to the pipeline using branch predictors, sophisticated translation lookup buffers, etc. And here the third level of cache L3 was also introduced, and of course, hyper-threading support was there. Some of the design considerations here was that hyper-threading was again introduced in this family because there were several applications which demanded larger number of threads which started to appear. Because of that, this hyper-threading concept was again introduced here. And all the cores, they were placed on the same integrated circuit die. It was a single chip and the first 2 levels of the caches were private to the core, while the L3 cache was shared among the core. So, here the number of cores were either 2 or 4, both these 2 kind of families were there. Okay. Then let us have a brief look at the Sandy Bridge architecture which came after that. So, here some vector extensions were made to the processor. Some features which were earlier present in vector or array processors, because of application demands, some of these were integrated in the processor itself. Okay. There was a separate engine which is called AVX, Advanced Vector Extension. Secondly, the graphics unit, the GPU was also integrated on the same die. There was a feature, this is called turbo boost technology, which also appeared. Now, turbo boost technology is something like this. The system can automatically check the temperature of the chip. If it finds that the temperature is not too high, then at least for a few seconds it can go in a turbo execution mode, where the frequency will be increased, of course, heat generated will also be increased and you can run your programs much faster. So, for a few seconds you can move to a turbo boost mode and you can execute some applications very fast, but you cannot do it in a sustained manner because the temperature of the chip will be going up quite significantly. And inside the die there was some ring kind of interconnects which was proposed, which connected the cores and also the memory management unit, and the memory controller was also on chip. Then the Haswell architecture, which is one of the latest. Here the branch prediction was made much more sophisticated using lot of hardware support, and there was some improvement in the front end, like the TLB and the cache misses. There was some speculative processing here. Cache misses were handled in parallel, multiple cache misses were handled in parallel to hide the individual latencies, and as I said, branch prediction was improved to a great extent. for the load store unit, there were much deeper buffers. You could fetch larger number of instructions, keep it in a buffer, and from the buffer you can issue them to the pipeline as and when required. Suppose you have 16 instructions in a buffer, you can decide out of those 16 which one instruction to execute next. So, you can have out of order execution also. So, here you have larger number of execution units, it is actually highly superscalar. The execution units are made more efficient, latencies are shorter, and again to support this increased speed, the load store bandwidth is also increased. Now, let us look at this picture. This picture actually illustrates the Intel's philosophy of developing the newer generation of the processor. This is called the Tick-Tock development model. Now, the idea of Tick-Tock development model is like this. Intel comes up with a new architecture based on the present fabrication technology. Okay? This is one. This is called Tick. This is called Tock. New architecture, Tock. Then it moves to Tick, means the same architecture is re-implemented using a better fabrication technology. This is Tick. Then in the next generation you again move from Tick to Tock. That means a new architecture family with the same technology. Then again Tick, a better technology comes, you move the same architecture with a better technology. So, you see just in this diagram, Merom was one of the older architecture. This was fabricated using 65 nanometer technology. This was Tock. Okay. Now, the same microarchitecture was moved to a new process. This was given a different name. This was called Penrene. The same architecture was refabricated using 45 nanometer technology. This is Tick. Then in the next generation, a new microarchitecture was proposed in the same technology, 45 nanometer, same. This was called Nehalem. Then we moved to a next generation which was the same microarchitecture, but with a better technology, 32 nanometer. This was called Westmere. Then new microarchitecture with the same technology, 32 nanometer, this was called Sandy Bridge. You move on to the new process, 22 nanometer, this was called Ivy Bridge. Now, a new microarchitecture based on 22 nanometer, this is Haswell. So, like this, Intel likes to use the Tick-Tock kind of an architecture because it comes up with some architecture advancements, implements it with the present day technology, let it run for some time. By that time, some newer technology of fabrication is available. So, port it to the newer technology. So, in this way, it just advances. So, with this we come to the end of this lecture, where we very briefly looked at a couple of case studies. One was that of a graphics processing unit, and the other was the evolution of the Intel family of processors. Thank you.